Also, by drawing the graph of the function as the conditions are given, we can show easily fx will be continuous. Now we find LF1 and F1 both 2, and already we have mentioned the condition of continuity of the function fx at x equal to 1 is this one. Therefore, our f1 must be equal to LF1 as well as f1. Now the second one, fx is defined as this. First we calculate left hand limit, then right hand limit, then value of the function. L f0 limit x tends to 0 minus fx, that is equal to limit x tends to 0 minus fx means here minus x, therefore value is 0. f0, from this f0 is 0, r f0 limit x tends to 0 plus fx. See this, x lies in between 0 and 1 means if x tends to 0 plus, this is to be taken for fx. Limit x tends to 0 plus, that is equal to 0. Therefore, LF0 is equal to f0 is equal to rf0. fx is continuous at x equal to 0. Also, by drawing the graph of the function as the conditions are given, we can show easily fx will be continuous. Now, for x equal to 1, for x equal to 1, LF1 limit x tends to 1 minus fx, limit x tends to 1 minus, means this is to be considered x1 f1, that will be obtained from this one, 2 minus x at x equal to 1, that is equal to 2 minus 1, 1, r f1 limit x tends to 1 plus fx, limit x tends to 1 plus, when x is greater than equal to 1, value of fx is this 2 minus x, that is 2 minus 1. Thus we find LF1, F1 and RF1. Therefore, LF1 is equal to F1 equal to RF1. That means fx is continuous at x equal to 1. If we draw the graph of this function, we will see there is no gap, or there are no gaps at x equal to 0 as well as at x equal to 1. By drawing the graph of this function, we can also verify the function is continuous at the points x equal to 0 and x equal to 1. Now I move to number 3, problem number 3. I will draw the graph of this function and show what happens. Number 3, fx equal to mod x by x when x is non-zero and equal to 0 at x equal to 0. We calculate L if 0, that means limit x tends to 0 minus fx. In this condition, what we see, when x is not equal to 0, fx is this, that means limit x tends to 0 minus mod x by x, that is equal to limit x tends to 0 minus mod x. Already I have discussed that matter. Value of the given number or absolute value of the given number, modulus of the given number. In case of x negative, that will be minus x by x, that is equal to minus 1. Since x is non-zero, we can cancel it and get the limiting value minus 1. If 0 equal to 0, this is given, and Rf0, limit x tends to 0 plus fx, that is equal to limit x tends to 0 plus mod x by x, and mod x, when x positive, that will be x, limit x tends to 0 plus x by x, that means 1. What we find, left hand limit is minus 1, right hand limit is 1, and value of the function at the point x equal to 0 is 1. That means these three values are different. Therefore, Lf0 is not equal to f0, that is also not equal to Rf0. Therefore, the conclusion is fx is not continuous at x equal to 0. This is theoretical approach. Now let us draw the graph of this function. One thing, here we have to draw the graph without using graph paper. For that, on the plane sheet, you first take two mutually perpendicular lines. Horizontal one is x-axis, already you know, and vertical one is the y-axis. Their point of intersection is O. Now, with the help of your scale, you scaling first. You scale on the x-axis as well as on the y-axis. Already we have calculated left hand limit LF0, limit extends to 0 minus mod x by x, that is equal to -1. That means when x is less than 0, when x is positive, the graph is indicated by this ray. We name like this. When x is less than 0, AB ray A represents fx equal to 1. When x is, this is greater than 0, fx equal to 1. When x less than 0, CD C is excluded 0 minus 1. Shows fx minus 1. And fx equal to 0 when x equal to 0, the graph consists of the ray AB, the rays CD and origin. Now what we find, that there is breaks at the point x equal to 0. At x equal to 0, value of fx is 0, 0. When x greater than 0, value of fx is 1. When x less than 0, value of fx is minus 1. And y indicates y is equal to fx. Thus we find there is gaps at x equal to 0. From the graph, it is understood that the function fx is discontinuous at x equal to 0. The comment will be, from the graph we find there is a break, or you can use the term gap. There is a break of y equal to fx. Therefore, fx is discontinuous at x equal to 0. According to the given condition, we have drawn the graph and we find the graph consists of the rays AB and CD, where A is excluded 0, 1, C is excluded 0, minus 1, and rays AB ray as well as CD ray are parallel to the x-axis. As fx or y equal to constant, that will be parallel to x-axis, we have drawn the graph and see that there is break at x equal to 0. You see 3 different values. When x is positive, that means greater than 0, it starts from A. When x less than 0, the graph starts from C. C is excluded 0, minus 1, and when x equal to 0, that point is lying at the origin. Therefore, there is a gap. Therefore, from the graph, we conclude fx is just discontinuous when fx is defined as this. Now, I have taken this example. The function fx is defined like this when x is less than or equal to 1, fx equal to x plus 1, and 3 minus ax square when x greater than 1. And it is given that fx will be continuous at x equal to 1. For that, we have to find the value of a. This value of a is to be found. Now, fx will be continuous at x equal to 1 if F1 is equal to Rf1. We calculate Lf1 limit x tends to 1 minus fx limit x tends to 1 minus, when x is less than 1, value is x plus 1, the value will be 2. F1 from this condition we will get 1 plus 1, 2, and Rf1 limit x tends to 1 plus fx limit x tends to 1 plus value of fx in this case is 3 minus ax square. Finally, it will be 3 minus a. Now, we find Lf1 and F1 both 2, and already we have mentioned the condition of continuity of the function fx at x equal to 1 is this one. Therefore, Rf1 must be equal to Lf1 as well as F1. Since fx is continuous at x equal to 1, therefore Rf1 already we have mentioned. For finishing, we are mentioning here 3 minus a will be equal to 2. From that, a equal to, therefore a is equal to 1. That is the answer. Here I have discussed one more sum. Next I move to sum number 5. at the function fx is that will be continuous, fx will be continuous at x equal to 1 if LF1 is equal to RF1 is equal to F1. Now first we note fx, that is equal to x square minus 1 by x cube minus 1, numerator is x plus 1 into x minus 1, and denominator is x minus 1, x square plus x plus 1. We note that if x be 1, then value of x minus 1 will be 0. We cannot divide both numerator and denominator by x minus 1 if x equal to 1. That means fx is undefined at x equal to 1. Now let us calculate LF1. In that case, I write like this: if x is not equal to 1, then fx will be equal to, in that case we can easily cancel from numerator and denominator x minus 1, then value will be x plus 1 by x square plus x plus 1. Therefore, in that case, both left hand limit and right hand limit will be equal, and left hand limit and right hand limit will be equal, and that limit is calculated like this: limit x tends to 1 fx, limit x tends to 1 x plus 1 by x square plus x plus 1. Putting finally x equal to 1, the value will be 2 by 1 plus 1 plus 1, 2 by 3. As per condition, fx will be continuous at the point x equal to 1 if value of f1 be equal to each of values of LF1 and RF1. Therefore, fx will be continuous at x equal to 1 if f1 be equal to limit x tends to 1 fx, that is f1 is equal to 2 by 3. First, we have shown fx is undefined at x equal to 1. Now, given that this function is to be continuous at x equal to 1, for that, first of all, I have calculated the limiting value of fx as x tends to 1, and we got the result 2 by 3. Now, fx will be continuous at x equal to 1 if the value of the function at x equal to 1 be equal to the limiting value of fx as x tends to 1. Using that concept, we got if1 equal to 2 by 3. Hence the problem is solved.